Dear students, welcome to the Physics Virtual Lab for Grade 11. We are Faculty of Physics at the Delhi Public School, Bangalore East. I'm Anand. I'll be doing the narration and my colleague Mr. Murthy Kanchala will be demonstrating the procedure. This is the fifth experiment in this series and the aim of this experiment is to determine the force constant of a helical spring by plotting a graph between the load and the spring extension. The apparatus required for this experiment are the following. We need a helical spring, a rigid support to hold the spring tightly, a hanger weighing 50 grams. In addition to the hanger, we need 5 50-gram slotted weights, a sharp pointer attached to a hook, a vertical scale to measure the spring extension. The theory behind this activity. When a force is applied to a spring, it responds with a restoring force that opposes the applied force. Magnitude of this restoring force depends on the extension of the spring. The spring extends until the restoring force equilibrates with the applied force. Normally, the restoring force increases with the extension, but not necessarily in proportion to it. However, when springs are specially designed such that the restoring force is proportional to the extension, it permits a variety of applications in which the applied force can be estimated just by measuring the spring extension, which is a quantity easy to measure than the force itself. We consider one such spring for which the restoring force is proportional to the extension. When the restoring force is proportional to the extension, we can write the restoring force as a constant times the extension. This constant of proportionality is called the force constant, and determining this constant is the aim of this experimental activity. Because the applied force equilibrates with the restoring force, we can as well write the applied force as the force constant K times the extension L. Applied force is nothing but the load applied. Therefore, if we graph the load with the extension, that graph must be a straight line and the slope of that graph must be the force constant. That's exactly what we are going to do next. In the next section, my colleague Mr. Murthy Kanchala is demonstrating how to measure the spring elongation for different applied loads. We have videographed this demonstration. I'm going to play that now. Please feel free to pause the video to record the readings yourself. First, with no load on the spring, adjust the vertical scale such that the point is positioned at 0. If we do this, there is no need to subtract the initial position from the current pointer position every time to find the extension. The pointer reading is the extension. Once the pointer is set to an initial value of 0, add the slotted weights one by one, adding 50 grams at a time. Add the hanger. The hanger weighs 50 grams. Pause the video and record the extension for a load of 50 grams. Add another 50 grams. Before you record the extensions, allow the oscillations to completely damp. Pause the video again and record the extension for a total of 100 grams. Extension for 150 gram force. Extension for a load of 200 gram force. Extension for a load of 250 gram force. And finally, extension for a load of 300 gram force. That is not the end. We have to record the extension during unloading as well and take the average of these two values as the average extension. Record the extension for 250 gram force. (200 gram force). Extension for 150 gram force. Extension for 100 gram force. Extension for 50 gram force. The point is now back to 0, and this completes the loading and unloading cycle. Once the data are collected, tabulate them as shown. Please note that we are not using SI units. We express the load in units of gram force. 1 gram force is a force equivalent to the weight of 1 gram mass. We express the elongation in centimeters. Next step is to graph the data. Carefully choose the scales for the x and y axis. Plot the data points. Draw a line that connects as many data points as possible. That done, choose any 2 points on the straight line and determine the slope of the line. Slope of the line is the force constant that we are trying to measure. Express your answers in units of gram force per centimeter. In this case, the slope of the straight line turns out to be 14.1 gram force per centimeter, and that is indeed the value of the force constant of the spring. In performing this activity, we have to exercise the following precautions. Loading and unloading must be done gently. Have patience and wait until all the oscillations damp completely before you read the elongation. Stay within the elastic limit of the spring. Measurements are always prone to errors, and I can think of a few sources of errors in this experiment as well. The support may not be rigid. If so, the spring slips and our measurement of elongation will be erroneous. The slotted weights may not have exactly the same value that they claim. It is always a good idea to measure their weight in a physical balance and use the exact value. While reading the pointer position, make sure your eyeballs are at the same level as the pointer, because reading it from above or below the pointer level will introduce parallax error. Now, before we wind up, I'll leave you with some points to ponder. Will the force constant be a constant for all values of load? Can you think of any application for a spring whose elongation is proportional to the load applied? This brings us to the end of this lab activity. Thank you very much, and I hope this activity attained its objective.